Hello, can you guys hear me? Out there in Zoom space? Okay, great. The camera's not working for some reason. Oh, well, whatever.
This is really short. Well, it's tapping the wall. That's tapping the wall. It's like tapping the wall. Tapping the wall. So you do it in section. To the wall. Or this is what you so this is means the funding cycle. So now your heights. So
Hey, hello. Oh, good afternoon. Hey.
so you're saying that Now you know that your other steps. Like if you could fit this shape itself, just so you know that you can change your values. As long as you
All right, it's 2:30, so let's go ahead and get started today. Good afternoon, everyone. How's everyone doing today? Good, good. No more janky ass DocCam anymore. We got Zoom to work on the computer, so we're good. We're good to go on that. Hopefully the audio is going to be better too. I was watching the recording from Monday, and the audio was a little bit stuck. So now that we have a legit thing here, hopefully that'll make it a bit better. Okay. So the plan for today is we're going to finish up our lecture notes on radial systems. And so I have a little bit to finish up of what we covered on Monday, and then we're going to talk about spherical systems. And then after that, I think probably for maybe the last 15-20 minutes, we'll start the next set of lecture notes, which is on fins, which I think are really interesting, topic for us to cover, because it's more practical than what we've been going over. All right, so announcements. Remember, our first homework assignment is due tonight at 11:59, and so make sure you're working on that. I have your next homework assignment ready, and so I have the PDF for that, and so I'm going to post that basically right after the homework tonight is due. Question?
So we can turn it online or in person?
Yeah, if you have it in person right now, you can turn it in right now. And then there were some questions about how I'm going to give feedback to you guys. So if you turn in your homeworks in person, then I'm just going to mark it with the red pen just like normal, and then hand it back to you when I'm done grading it. If you turn it in online on Canvas, then I'm going to use there's like a comment box next to where you submit your assignment. I'm going to give you feedback from there. So my policy is, so I used to grade every single problem for accuracy back when I first started here, and I had about half the workload as I have now. But now I don't have time to look at every problem. And so what I do is that when I go to sit down to grade your homeworks, I choose one problem at random, and that's the one I really check for correctness. And then everything else I just check for mostly completeness. And so if I can see that you did, most of the homework, you put a good effort into it, you didn't just write the question down, you actually try to solve it, then you'll get all the completeness points. And then the one question that I pick for correctness, then I'll grade that one, with a more fine-tooth comb. Yeah.
In regards to your homework format, do you want us to copy the question down?
It does help me just for the sake of clarity. At the very least, draw the figure in your homework. Just because then it helps organize stuff. Because Yeah, I mean, for a lot of you, your handwriting is pretty neat, and so it's not that big an issue. But for those of you who have a little messier handwriting, it does help. It does help me to see, all right, here's the figure for this problem. This is probably their work for that problem. So it just helps me with grading it and making it a little bit faster, and helps keep my feedback a little bit more helpful as well. Yeah. All right, any other questions I can answer before we get started for today? Okay. All right, so let's go ahead and scroll up and see where we left off. Okay. And so when we left off last time, we were discussing this idea of a critical thickness, right? Because we've been working with cylindrical systems this whole time, right? And there's this really interesting relationship when you talk about the radius of a cylindrical system, right? And so when you increase this radius, right? I should say the outer radius, right? And so we're talking about a hollow cylinder here, so it has an inner radius and an outer one. When you increase the outer radius, there are two things that basically happen. And so on the one hand, you increase the amount of material, and so there's you can think of it as an increased amount of mass in your cylinder. Okay. Because when you increase the outer radius, you're making your cylinder bigger, and just by making the cylinder bigger, you just have more mass that you can have. Okay. The other effect that happens that that is kind of unique to radial systems is that the surface area also increases. Okay. Okay. And that might seem obvious, right? And so when you increase, the radius, you increase the volume. Of course, the surface area is going to increase. That's not exactly rocket science, but it has really interesting effects on our thermal considerations. Okay, and so each of these two effects here kind of have two different kind of thermal consequences. Okay? And so the increased mass that you have by increasing the outer radius is of course going to increase the conduction resistance, because there's going to be more material. Just flat out, just more material for the heat to pass through. Okay, and so your resistance of conduction is going to increase. Remember, and that's given by that formula there. But this increased surface area is actually going to have an opposite effect, where it's actually going to make the convection resistance go down, just because you have more surface area on the outside. Okay? Because when we have convection, right? Convection is basically whenever we have a heat transfer that goes from a surface to a moving fluid. Right? If you increase the amount of surface area or increase the amount of space where the fluid can actually contact the surface, it's going to enhance that heat transfer and thus lower the resistance. Okay, and so you have kind of these kind of dual competing effects right here, where one thing goes up but the other one goes down. And so there's actually a sweet point where both of them are kind of minimized as much as possible. And that's known as the critical thickness. Okay? And so that's what we're going to go over today. And so in class, we're going to talk about the how we can solve for the critical thickness for cylindrical systems. But in the next homework, I'm going to have you run through the same process for a spherical system. So kind of make sure you're kind of paying attention to the details of this derivation. Okay, and so if we go to our basic setup here for a hollow cylinder, our thermal resistance, or our total thermal resistance, has two contributions. Okay? Okay, and so our equation for our total here is going to have one contribution from conduction. Okay, and then one contribution from convection. Okay, so these are just the two formulas that we talked about at the end of lecture on Monday. I've just kind of added them together into one equation. Right, so the first one is from conduction, the other one's from convection. Okay. This idea of a critical thickness, or you can almost think of it as like a critical radius, is that this thermal resistance is going to reach a minimum at some point. Okay. Okay. And so if we draw a graph, right? And so let's say that we have on the x-axis here, we have the outer radius RO. And then on the y-axis, we have the total thermal resistance, okay? The existence of a critical thickness means that this curve here, if I were to draw this curve, it has to be minimized at some point, right? And so it should reach something like this, okay? Where this point right here, where the thermal thickness is the smallest, this is the critical radius, or the critical thickness, okay? Because that's the point at where the thermal resistance is the lowest. And so if you think back to your calculus classes, you know, how do we, if we have kind of a function like this, or an equation, how do we find the minimum of this kind of function? And so the way that we would do that is we would just take the derivative, right? And so if we take the derivative of this R total and set it equal to 0, then that's going to tell us where the minimum radius is going to be, okay? And so in other words, what we're going to do is we're going to take this equation up here, okay? Take the derivative of that function with respect to RO, okay? And set it equal to 0, okay? And then from this equation, we're going to solve for RO. Okay. And this RO is going to be the critical thickness. Okay. All right, so let's go ahead and compute the derivatives. And so the derivative of ln of RO divided by RI divided by 2 pi KL. This is the only term that we're actually taking the derivative of is just ln. Okay. And so this is going to be 1 over 2 pi KL times RO, okay, minus, we have a minus that comes out because in this equation we have 1 over RO. Okay, so we have basically RO to the -1 power. And so we take the derivative of that, we have a minus that comes out in front. We have 1 over 2 pi H L RO squared. Okay. All right. Any questions on this so far about, you know, about why we're taking the derivative and how we got this equation so far? Okay. All right. And so now that we've set this equal to 0, we can go ahead and solve this for RO. Okay. So I'm going to take one of these parts and I'm going to move it to the other side of the equation. Okay. So I'm just going to add that to both sides. So we have 1 over 2 pi H L RO squared is equal to 1 over 2 pi K L RO. Okay. Yep.
What happened to the RI when you took the derivative?
So the RI, we assume it's going to be constant in this case.
Oh, right.
Remember, because the ln of RO divided by RI, this is the same thing as ln of RO minus ln of RI. And so in other words, we have two terms in that numerator. So we just split them up, take the derivative. Since it was a constant, we just got rid of it. Yep. Mhm. Okay. So now we have this equation and a bunch of these terms are going to cancel out. And so you can see here we have 2 pi on both sides. And so those are just naturally going to go away. We have an L on both sides, and so those are going to cancel out with each other. Okay. I'm going to take this RO squared on the bottom, and I'm going to multiply by both sides so it comes out on top. Okay. Then this K right here, I'm going to multiply it to the left side so it pops up right there. Okay. And so if we do all of those things, we get K over H is equal to RO squared divided by RO right? Of course, that's going to cancel out. And so we get RO, where the RO is the critical RO, is the ratio of the thermal conductivity and the convection coefficient. Okay. All right. And so if you have a hollow cylinder like this, and you take the thermal conductivity and you divide it by the convection coefficient on the outside, that's going to give you the radius at which your thermal resistance is going to be minimum. Or in other words, your critical thickness. Okay. And if you actually plot this, and so I kind of just made just a kind of a made up plot right here, but if you actually do plot it, it does actually look very similar to that. And so it has almost this kind of like bathtub kind of look. And so we have kind of a steep shallow end right here, and then kind of a more gentle rise over there. Okay? And the radius at which this happens, this is the critical thickness. Okay. All right. Any questions on kind of the end of this critical thickness? Yeah.
If our goal was to create a tube with the most insulation so that the hot liquid inside wouldn't, burn someone, wouldn't we want to maximize the total resistance instead of minimum?
Yeah. No, you're absolutely right. It's because in a lot of cases you do want to insulate it in those cases, but you have to think about kind of where you are relative to this critical thickness. And so let's say that you're kind of starting out in a region where there's just not that much insulation to begin with, and so you have basically no insulation. And so you have to be kind of aware that when you first start adding some insulation, you're actually making the thermal resistance go down, right? Because most of the time you start out with zero thickness, right? And so for a little bit of time, when you're adding that thickness, you're starting out on this part of the curve right here, where the kind of the effect of the increased surface area is kind of outperforming or it's being more significant than the increase in conduction resistance. It's only after you get past this critical resistance, you actually start to see a more beneficial effect to more insulation. Yeah, so you kind of have to be aware of where you are on this curve and just make sure you kind of get past that critical thickness so that you can keep adding insulation. Yeah. Mm-hmm. Okay, and so that's it for cylindrical systems. And so the next system that we're going to look at is spherical systems. Okay. And of course, since we're looking at spherical geometries, we have to look at spherical coordinates. Okay. And so the first thing I'm going to show you is the heat equation in spherical coordinates. Okay. All right. And so I'm going to give you the full equation first, but of course, a lot of these terms are just going to cancel out. Right. Oh, I should say in spherical coordinates, our primary variables are r, which is the radius. We have a polar angle, theta, and then we have an azimuthal angle, b. Okay. Right. So instead of r, z, theta, we have r, theta, phi. So we have two angular components instead of just one. Okay. First, we have all of these diffusion terms. Okay. Don't worry, a lot of these are going to cancel out. All right, so here's the full heat equation. and the spherical coordinates. Okay. For your viewing pleasure, although for most of this, we're not going to worry about it too much. Okay? Because just like we did with the Cartesian and just like we did with the cylindrical systems, we're going to apply a bunch of assumptions to this to make sure a lot of these terms cancel out. Okay. Okay. So I'll give people a second to kind of catch up a little bit. Okay. All right. So just like we did with the cylindrical systems, I'm going to go ahead and label each of these terms. Okay. And so these terms that I'm circling in black, okay, these are all the diffusion terms, right? And so those match up with the second order derivatives basically that we were working with before. Okay. This Q dot, of course, is our thermal production. Okay. And this one right here is our steady or unsteady term. Okay. All right. So even though the heat equation, it looks, mathematically it looks very different from our Cartesian version and our cylindrical version. It has all the same components. They just kind of take different mathematical forms because it's a different coordinate system. Okay. Okay. And so, of course, we can't solve this as it is because it's too crazy. And so we're going to apply assumptions. Okay. And let me color code these just so you know what terms I'm canceling out. Right, so the first thing we're going to do is we're going to make the steady state assumption. Okay. And so, of course, steady state, we're going to cancel out the unsteady term. Okay. The next assumption that we're going to make is that our heat flow is one-dimensional and it's only in the radial direction. Okay. And so this means that if we see any derivatives with respect to the angles, okay, we're just going to set those equal to 0. Right. And so that's going to be those two big terms right there. Okay. Right. Remember, and the primary reason we're getting rid of these is because we're assuming the temperature does not depend on phi or on theta. Okay. And so we're going to cancel those terms out. Okay. And for certain cases, when you can assume that there's no production or no generation, then we cross out this term here. Well, okay. But this one's only sometimes. So sometimes we'll leave it in. And I think we'll do an example later where we actually leave it in. But sometimes we can also take it out as well. Okay. And so under all these assumptions, we're left with the following equation. And so at first we're going to solve for the heat equation without any production, but later on we'll bring it back in. But if we get rid of production, then we're left with 1 over r squared ddr. Where again, I'm changing the partial derivatives here to regular derivatives, just because they're the only variable left. Okay. And we have that whole thing equal to 0. And so this right here is, I think, the simplest spherical heat equation that we can solve for without production. Okay. This is 1D spherical heat equation without production. Okay. So let's go ahead and solve this for a simple case. But before we do that example, are there any questions on how we obtain this? Okay. All right. So let's do a simple example. And we're going to do the classical one here. So same like we did in cylindrical case. Okay. And so let's say that we have a hollow sphere. Okay. Right, so this is a hollow sphere. Okay. We'll say the inner radius is Ri, the outer radius is Ro. The inner temperature is held at a temperature Ti, and the outer temperature is held at a temperature To. Okay. Okay. And so all the assumptions are the same as what we just gone over. Okay. And so let me formally list out the boundary conditions before we actually set about solving. All right. And so in this case, the problem actually gives us the temperatures at the two radii. And so they're both going to be specified temperature boundary conditions. And so we have T at Ri is equal to Ti. And our other boundary condition is T at Ro is equal to To. Okay. Okay. And so under those assumptions and with these boundary conditions, let's go ahead and compute what the temperature distribution looks like. Okay, and so we're gonna start with the heat equation that we have up there. So we have 1 over R squared times DDR times K R squared dt dr. Okay, is equal to 0. And just like we've done in the previous, for the previous couple of weeks up to this point, we're going to go ahead and integrate this equation and solve for T of R. All right, so the first thing we're going to do is we have this 1 over R squared that's kind of a little bit of an eyesore. And so let's go ahead and multiply it out. And so I'm going to multiply both sides by R squared. So we're left with DDR. And in fact, I'll divide by K too, because we're going to assume the K is a constant. Okay. And so what we are left with is DDR of R squared dTdr, okay, is equal to 0. And so we're going to integrate both of these expressions with respect to R. And so the on the left-hand side, that's going to cancel out with the derivative. And so on the left-hand side, we're left with R squared dTdr is equal to C1. Okay. Because remember, we're doing indefinite integrals here, so we have to add our arbitrary constant just to make sure we're all we're all good. Okay. Next, I'm going to divide both sides by 1 over R squared, or multiply by 1 over R squared on both sides. Okay, so just like we did up there. Okay, and so we're left with dTdr is equal to C1 divided by R squared. Okay. I'm going to integrate both sides of this equation by dr again. So that's going to get rid of this guy. Okay. Right. Is that good? Okay. All right, and so if we integrate both sides with respect to R, then on the left-hand side, we're left with just T of R. Okay. And on the right-hand side, what we're left with is integral of C1 over R squared. And so that's going to be a negative C1 over R plus C2. Okay. You good? But since we haven't specified the value for C1 yet, I'm just going to take this -1 and just kind of lump it together with C1. Okay. Just because if we don't have to deal with the negatives, it's okay to just not have to deal with it. Okay. And so we have this as our as our temperature distribution at this point. Okay. All right. Any questions on how we got here? Okay. Okay, and so now that we have our general solution, we can go ahead and apply the boundary conditions now. Okay. And so we have 2 of them. And so first one we have is T at Ri is equal to Ti. Okay. If we plug Ri into this equation, we have C1 divided by Ri plus C2. Okay. Next, we have T at Ro is equal to To. Okay. So C1 divided by Ro plus C2. Okay. Right, and so here are our two equations that we can use to solve for C1 and C2. I'm going to do the same trick that I did in cylindrical cases, where I'm going to take these two equations, I'm just going to subtract them. And that works because we have a C2 here that's kind of just by itself. And so when we subtract these two equations, we eliminate C2 from the equation completely. Okay. Okay. And then what we're left with is C1 over R1 or C1 over Ri minus C1 over Ro. And then all I did was I just factored out C1 because C1 was in the numerator of both terms. Okay. And then from this, we can divide both sides by that expression in the parentheses. And we get C1 is equal to Ti minus To divided by 1 over Ri minus 1 over Ro. So it's a little bit messy. We have quite a bit of fractions floating around. But this is our expression for C1. Okay. And so now that we have this expression for C1, we can go ahead and plug this back in and solve for C2. Okay. And so you can choose either of the equations that you want. And so I'm going to go ahead and pick the first one. Okay, so I'm going to go ahead and plug this back here. Okay. And if we do that, we get C1 over Ri. And so we have 1 over Ri multiplied by Ti minus To divided by 1 over Ri minus 1 over Ro plus C2 is equal to Ti. And so to solve for C2, all we have to do is we just have to take this and subtract it from that side of the equation. Okay. And so if we do that, we get C2 is equal to Pi minus Ti minus To all divided by 1 over Ri minus 1 over Ro. Okay. Oh, excuse me, sorry. I forgot to multiply this Ri through here. And so if we multiply this Ri through the denominator here, then we have Ri over Ri, okay, which is just going to be 1. Okay. And so this first term here is just 1. Okay. And the second term here is going to be Ri over Ro. Sorry about that. Okay. So now that we have our expression for C2, we have C1. We can go ahead and plug it back in to get our full solution. And so our full solution here is going to be 1 over R multiplied by C1. Okay. And so C1 is Ti minus To divided by 1 over Ri minus 1 over Ro, okay, plus Ti minus To all divided by 1 minus Ri divided by Ro. And so this right here is our full solution, okay, with all the C's plugged in for. But this solution here, it's a little bit of a mess. And so, there's kind of too many R's and too many T's kind of floating around. And so you can manipulate this equation, using some algebra just to get it in a little cleaner form. And so I have the details of that in the notes, but, just because in the interest of time, I'll let you kind of look over that and I'll give you the final solution. Okay? And so through the magic of algebra, what we get is kind of the cleaner version of this temperature distribution. And so what we get is T of R is equal to Ti plus To minus Ti multiplied by 1 minus Ri divided by R divided by 1 minus Ri divided by Ro. So this one here looks a little bit cleaner than the one up there. Just by a little bit. They're both still kind of a mess, but you know, better to have just a slightly less mess than a bigger mess. All right, any questions on this? Yep. Yep. So this is the form that's displayed in the textbook. So I wanted to show you to you in case you were referencing that. But if you were to leave it in this form up here, you know, that's okay. Okay. All right. And so now that we have this expression right here, let's take the derivative of this and plug it into Fourier's law. Okay. Okay. So remember, Fourier's law is given by Fourier's law is given by Q R is equal to minus Ka dt dr. Okay. And so now that we have T of R, we can go ahead and plug it in for that. Okay. Right. The other thing that we can plug in for is A, where A, remember, is the surface area. Okay. And so the surface area of a sphere is 4 pi times the radius squared. Okay. And so go ahead and plug in for I right there. Next thing we're going to compute here is dTdr. And so let me go ahead and do that up here. Okay. And so we're going to take the derivative of this expression here with respect to R. And thankfully, a lot of this is actually just going to go away. Okay. Because if we take, let me go ahead and just plug this in here. Okay. So we have ddr of Ti plus To minus Ti times 1 divided by Ri divided by R times 1 minus Ri divided by Ro. Okay. We know that when we take the derivative of a constant, it just goes to 0. And so the derivative of Ti here is just going to go to 0. Okay. This next term here looks pretty intimidating, but a lot of it's also just a constant. Because if you look at this term right here, okay, right, we kind of just ignore this thing in front because it's just a constant multiplier. Okay. And so this term right here, we have 1 divided by 1 minus Ri over Ro. This is also a constant, and so you know that goes away in the derivative. Okay. And so the only thing that we have here is this term. Okay. And so let me go ahead and write that out. So our only term that we're taking the derivative of is To minus Ti times minus Ri divided by R divided by 1 minus Ri divided by Ro. And so that's all that's left, you know, when we take the derivative and we get rid of all of the constants. Okay. And if you notice here, the only term that we're actually taking the derivative of is this one, right? That's the only R. All the other Ri's and the T's are just constants, and so they kind of just are coming along for the ride. Okay. And so if you compute that derivative, we have dTdr is equal to minus 1 over R squared times Ti minus To divided by 1 divided by Ri minus 1 divided by Ro. Okay. And so now that we have this expression for the derivative, we can go ahead and plug it back up here along with the surface area. And then we can go ahead and use that to compute the heat transfer rate. Okay, any questions on this? Okay. All right, so let's go ahead and plug that in. And so we have QR is equal to minus K times area, which is 4 pi r squared, okay, multiplied by dTdr, which we have just right above here. And so we have minus 1 over r squared multiplied by Ti minus To divided by 1 over Ri, 1 over Ro. Okay. Let's go ahead and simplify this a bit. And so we have r squareds here. And so they're going to cancel out. Okay. We have negatives here. And so those are going to become positives. Okay. The negative frown was turned upside down by the other frown. So now they're happy. Okay. And so if we apply those, then what we're left with is we have a K times 4 pi. So we have 4 pi K. Okay. And let me do it like this too. And I'm going to take this denominator here and kind of move it out in front. Okay. So this is going to be 1 over Ri minus 1 over Ro, okay, multiplied by the temperature difference Ti minus T. And so this is our expression for heat transfer in a hollow sphere, or heat transfer rate in a hollow sphere with prescribed temperatures on both sides. Okay. Okay. All right. And so I put this heat transfer rate in this form for for a very specific reason. Because if you remember, back from when we did Cartesian heat transfer, and even just even earlier today in this class when we talked about cylindrical heat transfer, we have an expression for our thermal resistance, right? Okay. And so remember, in general, this is even beyond spheres, right? If we have a thermal circuit, then the heat transfer that we can, or the heat transfer rate in that thermal circuit is equal to the difference in temperature between two nodes divided by the resistance. Okay? If we look at the equation that we just derived using Fourier's law, we have something that's very similar, right? So we have heat transfer rate, right, on one side of the equation. We have a difference in temperature, okay, just like that. And this last expression, that means that this last expression here, this has to be the thermal resistance, right? Or it's 1 over the thermal resistance. And so if you kind of make that connection, then the thermal resistance of a sphere is equal to 1 over Ri minus 1 over Ro divided by 4 pi K. My mouth said 4, but my mind said 2. Okay. All right, so this is great. And so, the fact that we can have a thermal resistance expression here for spheres means that we can apply the exact same, thermal circuit solution methodology that we've had been before, but for spherical systems. Okay. And so for cases where you have kind of a layered sphere, or where you have kind of more than one layer of a sphere that you want to solve for the heat transfer from, you can just use the thermal circuit, right? And so, just as an example, let's do, let's say that we have a multi-layered sphere. So you have like a gumball, I guess. Okay. And so let's say this is the cross section of the sphere. Okay. Okay. Right, and let's say, let's say that we're interested in computing the amount of heat that passes through the sphere, right? But if we have 4 different layers like this makes it kind of a pain in the butt to use it with the heat equation. Okay. But in multi-layered systems like this, a thermal circuit does a really nice job of making it simple for us, right? Because what we can do is we can take each layer here and represent it as a thermal resistance. Okay. Right, and so instead of having something like this, what we'd have is, a system with 4 resistors, just like that. Okay, where each resistor is given by this expression right here, with the appropriate radii, inner and outer radii, that's used for it. Okay. All right, so that really simplifies this. And so if you have kind of a multi-layered system like we have here, then you can solve for the heat flow through it very, very easily. Okay. And one of your homework problems is actually going to be exactly like this. Okay. And so what I'm going to ask you to do in the homework problem is to compute the amount of heat loss that you have from your eyeballs. Okay. And so it's an interesting kind of thought, because the human body is kind of naturally at a higher temperature than everything on the outside, usually, unless it's a day like today where it's freaking hot outside. And so because of that, you're kind of constantly losing heat from your body just by virtue of heat transfer. And so in that problem, I want you to see, how much heat loss you actually have from your eye. Okay. And it kind of comes up to and kind of the motivation for this problem is actually a conversation I had with a friend of mine in college, where alcohol may or may not have been involved, but we're thinking of innovative ways to lose weight, and he asked me, since we're losing heat from our body, if we keep our eyes open the entire night, if we train ourselves to sleep with our eyes open, can we lose weight by doing that? And so that problem was kind of motivated by that. And so, I won't spoil the answer, so I'll let you do the problem and find out for yourself. But that's kind of where that motivation came from. All right, any questions on thermal circuits for spheres? Okay. All right, so so I actually do have one more example here in the notes on spheres, although we are running a bit behind, so I won't be able to run through the whole thing, but I at least want to get you started, because it's another kind of interesting application. Okay. All right, so I'm not going to run through the whole thing, but I will show you kind of how to set it up, and then you can look at the rest of the details in the notes. Okay. And so this example is one where I'm asking you to solve for the temperature distribution in a solid sphere with thermal generation. And so we have a sphere here. It's solid. And so there's no inner radius, so there's only one outer radius. Okay. Okay. And there's going to be thermal generation. And there's going to be convection cooling as well. Okay. Oops. Okay. And so in this problem, this is a heat equation type problem. And so here you're going to solve the heat equation. For the temperature distribution in the sphere. Okay. And so the thing that's different about this problem is that we have thermal generation, and so you're going to have to leave that in the equation. Okay. And the other kind of complicating thing about this example is, the fact that we have a solid sphere, and so we don't have any inner radius at all. Okay. And so that kind of presents an interesting problem when you're listing out the boundary conditions. Okay. And so the first boundary condition is you can take it directly off the diagram. We have convection cooling on the outside. Okay. So let me assume the radius of the sphere is r. And so what r is, little r is equal to big R, what we have is minus k a dt dr at r is equal to big R. Okay. This is equal to h times a times t at big R minus t infinity. Okay. So that's just a convection type boundary condition. And so you know, it's a little bit of a hassle to plug into, but you know, but once you have the temperature distribution, you just go ahead and plug in. Okay. The other boundary condition is not obvious, but we did do an example like this on Monday with the solid cylinder, right? And so the other boundary condition, if you can call it that, is the fact that our temperature solution has to be valid at little r is equal to 0. Okay. Okay, because r is equal to 0 is actually in our domain. Okay, and so we have to solve for the temperatures there. Okay? And I'll give you a hint. And so this is not the solution to this problem because there's generation. But if you remember from the example we did earlier, you know, if there's no generation, then we have a term which is C1 divided by R, right? And so if you plug in r is equal to 0 here, right, then what does this term do? So you have one over, you have some constant over 0, and so this goes to infinity and beyond, right? And of course that can't happen, right? So you know, there's the inside of a gumball is not at infinity temperature, right? And so, you know, in order for that to be valid, then we have to kind of get rid of any term that's not valid at r is equal to 0. Okay. Okay. All right, and so I think that's all I wanted to say on that problem. You know, so the only thing, you know, and you can look through the notes, do a pretty good job of being detailed with it, but just, you know, make sure that you keep the thermal generation term in the heat equation when you're doing your integration, and make sure you get rid of this this 1 over r term because it's just not going to be valid. Okay. Any questions on this before we move on to fins? Okay. All right, and so that's everything with radial heat conduction. And so the next thing that we're going to go over is the formal name for this is heat transfer from extended surfaces, but I think what everyone kind of knows them for is fins. Okay. Okay. All right, so let me start this section by saying that, you know, up until this point, you know, one big assumption that we've been making is that our heat transfer has only been occurring in a single direction, right? And so we've only just been looking at 1D heat conduction. Okay. And so all the heat is just going in one direction, right? And so if we look at a Cartesian case, okay, and so let's say we have multiple layers of solid here, then the heat is just traveling just one direction through this wall. Okay, so we have Q, 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 Q. Okay, or even in radial systems too. And so in radial systems, you know, we have, you know, a cylinder. Let me just draw a cross section of a cylinder. Okay. Same thing for the cylinder. And so we assume that the heat transfer is just going one dimensionally out, just like that. Okay. 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 And so the key feature with this, you know, if we consider just kind of one slice here on either side, okay. one key feature that we've kind of been implicitly assuming is that the cross-sectional area for conduction is the same as the cross-sectional area for convection, right? And so if you have convection cooling that's on the outside here, right? Then, when heat comes out here through through conduction, right? And so when heat passes through this surface right here, it's using the exact same surface area for conduction as convection, right? So conduction is going through the surface through one cross-sectional area. That same cross-sectional area is being used by convection, okay? Okay. And so when we compute Fourier's law, the A is basically, there's only one A, okay? And so we have Q is equal to minus K times A dt dx. Okay. Right. And so when I say that, conduction and convection use the same area, then no matter, if we're doing Q of convection or Q of conduction, this area, this A here is exactly the same. Okay. All right. And so, up to this point, that's been totally fine, right? So there's nothing wrong with that. And in fact, a lot of interesting practical situations can fall into this category. But it's not every single thing that's out there. Okay? And so for this particular unit, I want to consider situations where conduction and convection are actually perpendicular to each other. Okay. And so visually, it looks something like this, where, let's say that we have some extended surface, okay? Let's say we have a pillar, okay? And so let's say that we have a difference in temperature on one end of the pillar and the other, okay? And so since we have a difference in temperature coming from top to the bottom, we know that there's going to be some conduction heat transfer. Just naturally there's a there's a temperature difference between those two areas. Okay? But if this surface here was exposed to air or to some fluid, right? So let's say we have some fluid that's hitting the pillar. Okay, and so the fluid has some ambient temperature and some convection coefficient H. Okay. And let's say the ambient temperature is lower than that of the pillar, okay? Then of course, this pillar is going to be losing some heat to that fluid, okay? Right, and so you would have Q convection that comes out the sides, okay? Right, and so even from the simple diagram, you can see here that we have conduction that's going vertically up and down, and convection that's going horizontally across. Just because that's just the geometry of the situation. Okay. And so in these situations where the areas are not the same for conduction and convection, this kind of falls into this category of heat transfer from an extended surface or heat transfer from a fin. Okay. All right. Any questions on this? Okay, and so that's kind of the mathematical and kind of physical principle behind what we're going to discuss in this unit. But what's the practical implication, right? So where do you see these kinds of extended surfaces? And in fact, why do they even exist? Okay. All right, and so to answer that question, I'm going to draw two situations for you, okay? And so I'm going to draw just a flat wall. Okay. Okay. And let's compare this to the same wall, but let's stick some fins that's coming out of it. Okay. One more. Okay, so this is a fin, a wall with some extended surfaces. Okay. Right. All right, so what's the difference between these two situations, right? And so on the one hand, on this flat wall right here, the amount of heat transfer that you can get out of it is limited by just the area of the wall. Okay. On the right, and maybe I should have drawn this better, just so that they, assume that they have the same heights. Okay. Right. And so on the situation on the right, you have a wall that occupies the same amount of vertical space, right? But we've added these fins to it, right? And the primary effect that these fins have is that they increase the amount of surface area on that surface. Okay. And what do we talk about surface area at the beginning of class today, right? So the more surface area that you have on your solid or on your surface, the more convection heat transfer that can occur. Okay. Sorry. And so the more surface area that you have, basically it's going to enhance convection heat transfer. Okay. Okay. And so if you have a fluid that's flowing past this surface, okay, right, then having these fins or having these extended surfaces is going to enhance the amount of heat that gets transferred from the solid to the fluid. Okay. All right. So why would you want this? And so why would you want to enhance the amount of heat loss from your surface? Well, there's a lot of or a big portion of thermal engineering has to do with effective cooling of certain hot parts. Okay. Okay. And so, let's say that you're designing the chassis of a car, right? Or maybe or even just the exterior of an engine, or even more micro in a more micro sense. Let's say that you're designing kind of the thermal sink of like a computer, right, or some kind of computer chip. And so in these situations, your objective as the thermal engineer is to try to offload as much heat as possible, because your part, say it's like an engine or say it's like a computer part, it's going to be generating a lot of heat. Okay. And so that heat that it's generating, once it reaches a certain point, it can actually start to melt the components in your device. So it can actually melt things like your engine parts or even your computer. And so in order for the device to function properly, you need to offload that heat as quickly as possible to keep the temperature under control. Okay. And so a lot of the practical situations that we're going to see in this unit are those kinds of situations where you're trying to enhance cooling as much as possible. Okay. And so to that end, what we're interested in as engineers that if we design a fin or if we design an extended surface, how much heat we want to compute how much heat is being lost from that fin, just so that we can help design it. Okay. All right, and so to that end, we need to have an equation for that. Okay, and so this next equation, its roots are still in the same heat equation. It's just that it takes a different form because of the whole perpendicular heat transfer that we talked about earlier. Okay. So before I do that, are there any questions on this? Okay. All right, so the next thing we're going to do is we're going to talk about the heat equation for the fin, or the fin heat equation. Okay. And just like I did for the previous unit, I'm not going to go through the whole derivation just because I think that would take kind of a long time. But I did want to talk about how it's derived. Okay. All right, and so kind of the most generic fin situation would be something like this. Okay. And so let's say that we have an extended surface coming from the fin. Okay. And let's take out a slice from that fin. Okay. And so if we take this slice and bring it out here, okay. Notice how I've drawn the fin to be tapered on purpose. Okay, so the cross-sectional area is generic at this point. Right, and so if we take a differential slice of the fin, we can go ahead and compute, or we can go ahead and quantify, all the heat transfers that's coming in and out of this fin. Okay, and so on the one hand, we have conduction heat transfer coming in from the base. Okay, so this will be Q conduction in. Okay. And on the other side, we have conduction heat transfer that's coming out. Okay, so we have conduction coming in, conduction coming out. And they may not be necessarily the same, because convection is occurring as well. Okay. And so at the same time, off the sides of this slice, we have convection heat transfer. Okay. Okay. Right. And so we have conduction coming in. In this case, in the horizontal direction, we have convection going out. From convection, okay, in a perpendicular direction. And if we perform an energy balance, okay, if we perform an energy balance, then we know that the sum of all these heats have to be, all these energies have to be conserved. Okay, and so if we perform that energy balance together with Fourier's law, for conduction, and Newton's law of cooling for convection. Okay. And so we basically plug in for our Q expressions here. Okay. Then we end up with the following equation. Okay. And again, most of these details I'm going to leave out, but I did want to show you kind of, how this equation is derived, just 'cause I think it adds some context to the different terms in the equation. All right, and so the ending equation looks something like this. And so we have d squared t dx squared plus 1 over a sub c times dac dx. And I'll define all these terms in a second, but let me just go ahead and write out the whole equation first. That's multiplied by dt dx. Okay. Then we have 1 over ac times h over k times d as dx. Okay. And this is going to be multiplied by t minus t. Okay. And the whole thing is going to be equal to 0. Okay. And so this right here is the fin, or you can think of it as the extended surface heat equation. And so just like our normal heat equation, the objective for this equation right here is to solve for T, right? And so if we solve this equation effectively, we'll get the temperature distribution within the fin, right? And then from that temperature distribution, we can compute, what the heat transfer rates are, into and out of the fin. All right. So let's go ahead and define these terms, because there's a lot of new variables here that we haven't seen before. Okay. I'll start from the left and go right. Okay, so let's look at this term first, right? So we have a d squared t dx squared, and so this is probably our most familiar phase so far, because if you remember from Cartesian heat transfer, this basically just represents the spatial diffusion of temperature through conduction down the length of the fin. Okay. Okay. And so that first term right there is just pure conduction. Okay. So just like we have in our Cartesian heat equation. So let me use a different color for this one. Let me use green. Next, we have this term right here, and the key term in here is AC. Okay, and so what AC represents? AC is the cross-sectional area of the fin. Okay. All right. And so the key term here is actually this derivative term right here. Okay. And so this is kind of an extra term that comes out that accounts for the fact that our cross-sectional area might be changing along the fin. Okay. Right. And so if you have a tapered fin, or if you have a fin that's that's becoming wider, then there's going to be some differences, or that's going to have some kind of effect on the temperature and the heat transfer rate. And so that's what that term there, that's what that term represents. Okay, and the last term that we have here is, of course, this one right here. It's the only term that has our convection coefficient H. Okay, and so what this term in its entirety represents is the convection heat transfer off the lateral surface of the fin. Okay. Or the key variable here is AS. Okay. So AS here is the lateral surface area. Okay. And so again, we have kind of a big, kind of long equation right here, but we're gonna simplify it a bit using some assumptions. All right. Any questions on the thin heat equation here? Okay. All right. So we have a couple of minutes, and so let me just talk about some of these assumptions, and then we'll pick up the solution on Monday. Okay. And so the first key assumption that we're going to make, which is only really relevant for this class, is we're only going to consider situations where the cross-sectional area is constant. Okay. This means that if we take the derivative of AC with respect to X, then this is going to be 0 in our cases. Okay. And so we're only going to consider, constant cross-section fins. Right? And so that helps us out a lot, because, what that does is that this takes this entire second term right here and just kind of gets rid of it. Okay. And so that's huge. And so that helps us out a lot. Along that same kind of using that same logic, then we can actually come up with an expression for DAS of X as well. Okay. And so this is going to be equal to P, where P here is the perimeter around the fin. Okay. And so if you have a fin that looks like this, okay, then P would literally just be the perimeter around here. Okay. And so that simplifies our last term. And so in this last term here, instead of DAS dx, we just plug in the perimeter P, which is just a constant. Okay. All right. And so with those simplifications, then this is going to simplify our equation greatly. Right. Then what we get is d squared t dx squared minus HP divided by KAC multiplied by P minus T infinity is equal to 0. Okay. Right. And so this is a much more manageable form of the fin equation, that we're going to solve for on Monday. Okay. Because what this is an ordinary differential equation with a single constant here. Okay. And we can solve this, very easily using our knowledge of second order ODEs. All right. Any final questions before we wrap it up for the week? Yep.
So we're just not scrolling back up.
Yep. 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 Right. So I basically made the substitution where, I started from this equation up here, and this term right here, DAS dx, I just plugged in the perimeter for that term. And I'll explain that a bit more clearly next time, because I didn't have enough time today. But that result is also kind of a result of our assuming the cross section is constant. Yeah. But yeah, we'll go over that next time. Okay. All right. So that's all we got time for today. So thank you everyone for tuning in. Remember to turn in your homeworks by tonight. I don't see anyone in person, but if you do have it here, then I'm happy to take it. But if not, make sure you upload the PDF. All right, so I hope you guys have a good weekend. Thank you guys for coming as usual, and I'll see you guys on Monday. There's a stapler here, but usually it tricks people. I don't think anyone's put staples in this thing for like. Oh, there's staples. Okay. I was gonna say the stapler's been here for like years, but it's been empty of staples for like 3 years. So I guess someone finally put staples in. Yep.
You know when we plan to have our first?
So the first midterm, the date is in the syllabus. I don't have it off the top of my head, but we're on schedule to have that. Yep. Cool. Thank you. I think Kevin has it. Thank you.
You go over the homework.
I post solutions. So after I finish grading them, then I post. I usually don't go over them in class unless a lot of people want to ask for it. But I do post solutions.
Okay, thank you.
Yeah. Mhm. Okay.
She's already at the right time for
I do have to run, so I have something at 4 o'clock today. But if you send me an email, I can run through it. Yeah. Thanks, Kevin.
It's like over.
Thank you. You too. Zoom people, are there any questions? Okay.